Hi, everyone. This is the third recording of an Introduction to Statistics series. We had two other ones on two variables and different tests, statistical tests that were implemented in Excel, only in Excel. And this is going to move into a three variables. I'm Emil Koman. I'm with the Yukon Health and the Department of Public Health, and I'm here with my collaborator.
Yes. Hi, my name is Sachi, and I'm with the Department of Statistics at the University of Connecticut. And I'll be partnering with Emil to help explain this tutorial for the introduction of statistics in Excel. There's a few key things that we'd like to go over to make it more accessible to everyone. So just going to highlight those. So anything in orange highlights the instructions for that given portion of the tutorial. Anything in green highlights the input. Anything in blue highlights some derived value from the equations that we're using in the software. Anything in green highlights the results, and anything in purple is a formula that we've written out and you can use yourself. As you can see here, these are some of the formulas. These files will be posted to the tiny URL highlighted on the screen here, and you can also access the data on the OSF file. These examples use three continuous variables, and we will get into it with our first research question. So our first research question is, what is the effect of BMI on systolic blood pressure? And so essentially, we're using there's several different statistical models and analyses that can be applicable to three continuous variables. So you can see our research question to the left, and I'll
And
let.
we're gonna step back to remind you where these variables come from, which is we simulated them. So it's body mass index, hemoglobin A1C, and systolic blood pressure. But they actually follow real numbers, real distributions from some real data that you can see in the same Excel file. It's a different worksheet, DPP. It's an actual intervention. And because of that, they have some means like 36 for BMI, 6 for A1C. And there is a relationship between them that we built in when we simulated them. But for the purpose of this illustration, you have the formulas here if you want to check them out. But for the purpose of this illustration, we just have 10 cases, 10 people, so to say, with these values. But we simulated them so they are related. They are not just independent variables.
Absolutely. So then we use this cross product over here. You can see the highlighted purple formula. It uses the values on the left using BMI multiplied by HbA1c, and we can transpose those values to generate the covariances between the four variables. Those covariances are then used in this plot over here, and they can be used to calculate the relationship, the effect of BMI on systolic blood pressure. And I'll let Emil explain a little bit more here.
So the effect is going to be pretty much calculated by hand in Excel, following a formula that appears uh, a little scary, but it comes from some textbooks. This is an econometric textbook, green. But if you just look quickly, it's simply using the matrix or the vectors or the columns of the predictors. In this case, we just have one predictor in this one first example. And Y here is the actual outcome, which is the blood pressure one. So with these two, with some combinations, some multiplications, inverse, you can actually derive the regression coefficient at the end. We just implemented this in steps, so you can actually see that there is a matrix multiplication here. But it's very useful to see it happening in real time and to see how it actually, where is it coming from. But in the end, one number that we're interested in that we interpret here is this one, minus 0.286, which is the effect of BMI on blood pressure. So the higher BMI, the lower the systolic blood pressure. There is no test of statistical significance in here, but the results also match Excel data analysis option here, Excel can run a regression, a simple regression, and a multiple one. It's the same value. And it also matches another one that we generated using a software, which is Onyx. I'm just going to mention it briefly here, but it's a freely available website that software that can run simple regressions, but also more complex models. So the next one is
Yes, the next question is, what is the effect of BMI on systolic blood pressure, net of or distinct of that of HbA1c? So you can see that graphically demonstrated to the right in this little depiction. So we're seeing what is the effect of BMI on systolic blood pressure when when it's distinct of the effect of HbA1c on the blood pressure as well. So we've included these visual representations of our research questions as well. You can see this is the step-by-step method. This is also done by hand in a matrix, and we're using a slightly different equation over here. Um, and we've done this all by hand, and you can see Excel calculates the regression coefficient to be increased and changed in sign. So you can see now that it's 0.611710, and this matches quite well to what Excel has estimated for us. And I'll let Emil talk about that for a little bit as well.
And this one matches another output from the Onyx software, which is showing visually here the effect of one or the other one. Actually, I'm moving into the third one, and the third one is this one, which is what is this effect of BMI on systolic blood pressure varying also with the level of the second predictor, A1C,
Yes,
which
and
is
you can
depicted here.
exactly.
Yep.
That is the visual depiction of all our research questions because we want them to be more clear for anyone watching the video. And so you
And
can see we do the same method here. And yeah, go ahead, Emil.
and it's actually marked, the research question is marked in the visual because the main point or the main goal of this question is to figure out, is there such a modification of effect or interaction in this relationship? And therefore we have three predictors that we enter in the model. We have BMI, A1C, and the product of the two. And in the end, therefore, we have three different regression coefficients that we get out of this one. Our regression coefficient changed. It's a minus 12.8. It also matches what Excel can kick out by itself. It also matches what Onyx is giving us, minus 12.0, somewhat identical. So in this instance, we can not say, because there is no test of significance for the interaction effect, whether there is truly an interaction effect. But if there is, it means this effect that we had in mind, BMI on blood pressure, is changing. If it's changing, we don't know what number to talk about, but this is one effect at the level of the mean of this second variable. Anyway, the main point is that interaction is tested by adding a product term between the two predictors. But the next one is changing slightly because with the same three variables, the research question itself is changing slightly because now we're asking this one.
Now we're asking, what is the total effect of BMI on systolic blood pressure, including the indirect effect through HbA1c? So I think the visual depiction really makes this more clear here. You can see it depicted three different ways with the research question there. So we're saying the BMI has some effect on systolic blood pressure. BMI also has an effect on HbA1c, and HbA1c also has an effect on systolic blood pressure. But our research question is really asking, what is the total effect of BMI on systolic blood pressure? So that big blue arrow, the total effect, including the indirect effect through HbA1c. And you can also see this with path analysis. And like this is the kind of the tracing rule invented by Sewall Wright in 1921. And so we derive some of the results using this path analysis tracing rule here.
So this is a slightly different method. It still means we calculated the effects in Excel. We just had to come up with a formula like above in the regression case, but we're using this tracing rule, which is a handy tool, which simply uses the correlations between the variables. And that's why we have here the correlational matrix. We have all of them, the two predictors, the product of the two, and the outcome. And these are the correlations between them. With them, we can compute the ABC effects here, and then the indirect effect and the total effect. And that's what we get. The total effect is a minus 1.147. So that's our answer. The answer actually means there is an indirect effect, there is a total effect, and the difference between them is the direct effect. And we can move on to another case in which we're just complicating a little more. We're adding the interaction effect on top of this indirect effect, and we're not going to sit on this one too much. But again, the effects can be computed by hand from the same correlational matrix up here. And the correlations, by the way, can be computed straight in Excel. Excel has a correl function in here, and you just tell I want the correlation between these two columns or variables. So from this one, we're going to move into two last sections, which will include, on top of what we've been talking about, the three variables, a latent variable. So in this one, we have, is there a common cause or a latent factor? Let's call it bad health behind all of these three variables or health indicators. And this visual is actually showing this question. The research question is in these loadings, that's what they are called. But it means, are these three variables that we observe the result of something else behind them? And are these relationships strong or not? The results are shown in the ONIX part, but with our simple handy calculators, using just the correlation, in this case, between the three variables, we don't have an interaction term. So we pretty much have three numbers that we're using. There is a simple way to derive these loadings, to calculate them out of these three correlations. We did it here using the tracing rule. It can be shown, it's quite easy, but eventually they come out as these three numbers, which means that's how strongly the latent variable is impacting each of the observed variables. The three numbers are also replicated in ONIX in parentheses here, the standardized values.
Yeah.
So that's pretty much a factor analysis done by hand in Excel.
And the research question here is aimed more at the mean and the variability in the rate of change, so the slope. And also, we want to know if all the cases change the same depending on where they start off, and the derivation of the slope mean. We'll get to that in another session, but we're more focusing on the mean and the variability of the slope in these questions.
Yep. So the question, the research question formally sits in this visual in a different place than the factor analysis. Here it's still the three variables, but we're asking if we believe, if we change what we see these three variables to be, if we make them to look like time one, time two, time three, same kind of health variable, which is a little bit of a stretch. And that's what we did to the right here. We actually standardized the three variables so they have the same kind of distribution. So if that's the case, the question can be asked in terms of actual change, kind of in something, in some health status, let's say. It is a bit of a strange move, but if we're asking if there is a difference in the rates of change between 1, 2, 3, that can be captured by this rate of change or slope, which is a latent variable, and the variability will tell us, yes, people, these 10 different folks change differently. Some go up, some go down. And also whether people who start off initially, this is the initial level, change faster or slower than the others. The question is slightly different. This is technically a latent growth model, but we just wanted to show it because the derivation or calculation of the three main parameters, the variance of the slope, primarily the variance of the intercept and the covariance between the two, can also be done by hand using the tracing rule. So you don't need a software to do it. We did it here in Excel, and it matches except one of them, which we have to figure out why it doesn't, but maybe someone will find a solution in the comments. So this concludes this session. It simply says that these analyses use correlations, covariances too, between variables just to derive everything, and by hand. It can be done by hand in Excel, and it can be verified using more formal software.
Yes, and we would love to hear everyone's feedback in the comments. If there are certain topics you'd like to hear more about, we would love to hear that. Or if you have questions on this topic, we would also love to get back to you on that. So thank you for listening.
Yep, thank you.